The topic of this video is heat flow in non-uniform rod and applications of Sturm-Liouville eigenvalue problems. We will start this video by visiting the heat flow in uniform rod. For the non-uniform rod, we will explore three cases, one without source term, one with source term, and one with jump initial condition. Then we will visit other applications of Sturm-Liouville eigenvalue problems, vibrations of non-uniform string, and vibrations of a rectangular membrane. The generalized heat equation without a source term with the boundary condition and initial condition is shown on the right. The density, specific heat, and thermal conductivity are set to be constant to make this rod uniform along X. We can notice that this is an example of the regular Sturm-Liouville eigenvalue problem, and this figure visualizes its numerical solution as time t increases. Here, the left end stays at 0 and the slope of the right end stays at 0, satisfying the boundary condition. Also, the zigzag-like arc cosine initial condition quickly flattens out as the heat flows out to the surrounding through the right end of the rod. The overall heat in the rod gradually decreases to 0 as time becomes infinity. Now, let's compare the heat flow in uniform rod with heat flow in non-uniform rod. For the non-uniform rod, the parameters associated with the heat flow are functions of x. Since the parameters are always positive, the non-uniform case is also a regular Sturm-Liouville eigenvalue problem. We can observe that there are no big differences between the two cases. The positive parameters let the heat flow out of the rod through the right end and eventually decreases to 0, although the heat flattens out more quickly at the non-uniform rod due to larger parameters. What would happen to the heat flow in non-uniform rod if there is a source of heat? The source term, Q equals cosine x times U, is added to the heat equation, and the figure in the middle visualizes its solution. The solution seems to be like the no source case at first, but the solution becomes wavy due to the cosine nature of the source. We have seen from the figures that the solution starts with a zigzag-like initial conditions, but gradually flattens out as time increases. What would happen if the initial condition has jump discontinuity? The figure on the right has an initial condition with two jump discontinuities in the source term. We can observe that the solution becomes very similar to the previous example. Let's take a closer look at this case with the jump initial condition. This figure has a longer delay for the first time steps to better present what happens to the jumps. The solution starts with the initial condition of straight lines with jump discontinuities, and suddenly the solution becomes the Fourier approximation of this initial condition, and Gibbs phenomenon is observed near the jumps. Then we can observe that the heat equation instantaneously makes the solution to be smooth and the heat gradually decreases. Other examples of Sturm-Liouville eigenvalue problem can also be solved numerically. Here is a one-dimensional wave equation with boundary conditions and initial conditions. The figure on the left shows the solution to this eigenvalue problem, which is a vibration of non-uniform string. The higher dimension Sturm-Liouville eigenvalue problem can also be solved numerically. Here is a two-dimensional wave equation for the vibration of rectangular membrane, and the figure on the left shows the solution to this eigenvalue problem. The numerical method used for solving Sturm-Liouville eigenvalue problems shown in this video will be discussed in detail in a future video.